This is Module 5.07, Empirical and Molecular Formula Notes. We will only be doing empirical for now. So a molecular formula indicates how many of each type of atom are present in a single molecule. For example, C6H6 has 6 carbon atoms and 6 hydrogen atoms. Empirical formulas represent the lowest whole number ratio of elements in a compound. C6H6 reduces to CH. So let's take a look at some examples here. We have a molecular formula of C2H4. Both of these numbers can be divided by 2, so the empirical formula is CH. C3H6, both of these values can be divided through by 3. So this reduces to CH2, and I just saw an error up here. This reduces to CH2. C4H8, we can divide through everything by 4. So this formula, the reduced formula, is again CH2. And then C20H40, we can divide everything through by 20. So this also reduces to CH2. Notice that all of these molecular formulas have the same reduced or empirical formula. Let's look at another example to the side, C6H14. So we need to identify something that both values can be divided by, both subscripts, and the answer is 2. So our answer would be C3H7. So what I have here is a little bit of practice for you. So I would like you to write the values down. So pause the recording while you write the values down. All right, let's put in some answers. So we can divide both of these values through by 2. So you would have NO2. C6H12, everything can be divided through by 6. So you had a CH2. C2H2O4, everything is divisible by 2. So we have CHO2. Our last molecular formula, we can't divide through by anything. So in this case, it is C5H12. Sometimes the empirical and molecular formulas are the same. Now, empirical formulas are determined from lab data. So let's look at an example, and then I'll show you how to take that data and turn it into the reduced formula. So, a detective finds an unidentified powder by a dead body. The forensic lab identifies the compound as containing 16.4% arsenic and 83.6% iodine. What is the empirical formula? So here's how we approach this. We're going to assume that the sample weighs exactly 100 grams. If it weighs exactly 100 grams, then we know that we can just turn the percents into grams of the element. So now we can say that we have 16.4 grams of arsenic, and we have 83.6 grams of iodine. Now what we're going to do is we're going to find the moles of each substance. So we'll do dimensional analysis. So we have 74.92 grams of arsenic is the same thing as 1 mole of arsenic. And we calculate that and we get 0.219 moles of arsenic. Now we're going to do the same thing with the iodine. So iodine has a mass of 126.9 grams of iodine for every 1 mole of iodine. And that means we have 0.659 moles of iodine. So we're going to take these and we're going to turn them into subscripts. So we say that arsenic, 0.219, and iodine, 0.659. But that's silly. We can't have fractions as subscripts. We know they have to be whole numbers. So now what we need to do is step 3 or step 4, we need to convert everything into whole numbers. And we'll do that by dividing through by the smallest number, 0.219, because that guarantees that arsenic turns into a 1. And when we do the math, iodine is 3.01. And we look at that, we go, well, 3.01, that's pretty darn close to 3, and this is experimental data, so I can say that my formula is arsenic AsI3. And we learned in naming molecular compounds, since they're both nonmetals, that this would be arsenic triiodide. So here's another example. I want you to try it. A sample contains 26.8% silicon and 73.2% fluorine. What is the compound's empirical formula? And I know I've given you the answer, but let's see if you can do the math to make it work out. Remember, this means you have 28.6 grams in an imaginary sample and 73.2 grams of fluorine. So pause and see if you can get the correct answer. All right, let's work this out just in case you didn't get the correct answer. You have 26.8 grams of silicon, and our molar mass of silicon is 28.09 grams. And that would be 1 mole of silicon. And that is going to be equal to 0.954 moles of silicon. Now we do the same thing with the grams of fluorine. Dimensional analysis, 19.00 grams of fluorine, 1 mole of fluorine, and that is going to be equal to 3.85 moles of fluorine. Now we're going to turn those moles into subscripts. So we have Si 0.954, fluorine with a subscript of 3.85. We're going to divide through by the smallest to turn one of them into 1, so 0.954. And now we have SiF4. So when we did this, one of the subscripts turned into 1 and the other one turned into a whole number. But sometimes when you do these problems, you'll get one subscript that contains a decimal. So for example, you would have x1, y 1.33. I go, what do you do with that? Well, what you're going to do is to remember that we can turn decimals into fractions. So we're going to assume that you remember that 0.50 is equal to 1/2, and we can make that go away by multiplying by a 2. We're going to assume that you remember that 0.33 is 1/3 and 0.67 or 0.66 is 2/3. If we multiply these numbers through by 3, we will get either a 1 or a 2. And then you should also remember that 0.25 and 0.75 mean 1/4 or 3/4. So these you would multiply through by a 4 to get either a 1 or a 3. And then the last one is 0.2, 0.4, 0.6, and 0.8 are actually all represent either 1/5, 2/5, 3/5, or 4/5. So in this case, you would multiply through by 5. Now, some students, when they're faced with something that looks like this, take the shortcut of just going, well, let me multiply it by 2, let me multiply it by 3, let me multiply it by 4, let me multiply it by 5, and see what gives me a whole number. Because quite honestly, in this class, I'm not going to give you anything that goes beyond 1/5, okay? All right, so I've got some practice here. You try. Convert the following to empirical formulas. So I'll do the first one for you, and then you're going to give it a shot. So we have P1, O 2.5, and I go, oh, 2.5. Let me multiply that through by 2. So remember, I have to multiply both numbers through by 2. So I'm going to multiply this whole thing by 2. So I have P2O5. Let me also do the next one for you. C1 H2.67. Oh, that's like 2 2/3. So I'm going to have to multiply through by 3. So I'm going to pause here and let you do these. All right, so here are the answers that you should have gotten. You would have multiplied this first one through by 3, the second one through by 4, and the last one through by 5. So now we're going to apply it to a problem. A compound contains 25.9% nitrogen and 74.1% oxygen. What is the empirical formula? So let's go ahead and set it up. We have 25.9 grams of nitrogen, and we're going to convert that to moles of nitrogen. And that's 1.85 moles. Let's do the same thing. Let me draw your attention to that. I put N2, but this is just nitrogen. So I need to get rid of that N2. So I'm glad I made that mistake. That's a common mistake students make. When you're working these empirical formulas, don't use diatomics. All right, let's do the next one. Oxygen, we have 74.1 grams of oxygen. We're going to convert that to moles of oxygen. And we get 4.63 moles of oxygen. We'll convert these to subscripts. We divide through by the smallest value. And when we do that, we get N1O2.50. Do not round subscripts. Look to see if we can multiply through by something. And we look at that and we go, well, if I multiply through by 2, so I'm going to multiply by 2, and I'm going to multiply everything by 2, then I have N2O5, and that is my final answer. Let's take a look at this example. This one is a little bit different because they have given you grams instead of percent. But that's all right because we can convert grams directly to moles. And actually what they've done is we haven't had to convert grams to percent to grams. We get to go just directly. So we're going to work this just like normal. So we have 8.57 grams. Now remember, we're just going to write H, not H2, because it's part of a compound. So we have 8.57 grams of hydrogen. And we're going to cancel out the grams of hydrogen to convert to moles of hydrogen. And that's going to equal to 8.501 moles of hydrogen. I'll do the same thing with the nitrogen. 54 point, oh, I've got that wrong. Let me correct that. I inverted some numbers. I have 59.43 grams of nitrogen. Remember, this is not the diatomic because it's part of a molecule. 14.01 grams of nitrogen, 1 mole of nitrogen is equal to 4.24 moles of nitrogen. We write this out as the subscript. We have H, 8.501, nitrogen, 4.24 divided through by the small, and we end up with H2N as our answer. So if you're given grams directly, just go ahead, convert things to moles, and do what you've done previously. Here we have example 5, where you've got 38.7% carbon, 9.7% hydrogen, and 51.6% oxygen. In this case, you have 3 different quantities that you need to convert to moles. Other than that, it works just the same. So I want you to try this. So pause and work. So pause the recording and work the problem. I show the worked example here. Started with the 38.7 grams of carbon and converted that to moles of carbon, 3.22. Then 9.7 grams of hydrogen divided by 1.008 grams of hydrogen. And I want to bring your attention to one thing here. This number here has only 2 sig figs because the values are being recorded as percents. I did not round here. So one of the rules when you're doing long equations is don't round intermediate values. So I went one value past the decimal point so that I would not lose precision when I go to figure out what the reduced formulas is. So don't round intermediate values. This is a mistake that I frequently see students do, particularly when it's percent of hydrogen, because hydrogen is such a low molar mass. And then I figured out the moles of oxygen. You can see that it reduces here to C1 H2.99 0.996. The 2.99 and 0.996, we can round those because they're incredibly close to whole numbers. All right, that's it for empirical formulas. You can go do some practice on your own.